Hello and welcome to the lecture Convolution Neural Network Part 2. Here we are going to discuss the CNN model architecture. Namely, we first start with LayNet, then we discuss AlexNet, VGGNet and GoogleNet. As a part of GoogleNet, we will see the InceptionNet. This lecture will start with LayNet. Now, in this particular lecture, our basic agenda is that to discuss various standard convolution neural network, and here we start with LayNet. LayNet is a very old network. As you can see, it is proposed by LeCun et al. In 1998, and here the main architecture is like this. So this is the input image. Okay, so there is some convolutions layer there. Then there is some pooling layers is there, and there is some subsequent convolution and pooling is there. And as we understand, or as we can see here, that the image dimension are being reduced by the subsequent subsampling by the pooling. Then these features basically fed into the fully connected layer to get the output. So this is as a whole the LayNet. It is a very naive or basic kind of architecture. As you have seen, the convolution is basically they have 5 cross 5 kernels with stride 1, and in this pooling layer they used 2 by 2 subsampling with stride 2, and the basic architecture is like this. First we use a convolution layer, and then it's a pooling layer, that then again the convolution layer, and again a pooling layer, and then it is a kind of fully connected network. So this is a very old kind of architecture that may be the first kind of convolution kind of network. Next we'll come to the AlexNet, and this AlexNet is basically you can say the starting point of deep neural network. Mainly we can say the convolution network to outperforms this conventional machine learning networks. So it has been proposed by Grzybowski et al. In 2012, and there is you can say that as a whole it is a 8 layer, but within this layer there is some sublayers like this. So we'll see one by one how this AlexNet is being provided, the particular architecture. Now first of all, our image patch is dimension of 227 by 227, and there is a 3 channel image. Okay, so first convolution layer, as we can see here, first layer. So in this first level there is a 3 part. One is convolution, it's max pooling, and normalization or local normalization. Now the part 1 is this, you can say the first level. So first is convolution, so this convolution layer, then there is max pooling layer and normalization. Okay, so this particular thing, although this normalization is not shown here, but there is normalization. So this is basically local response normalization. So here you can see that this convolution layer, they use the 11 cross 11 kernel, is this, and we use a stride 4. So such filters, this 11 cross 11 filters, 96 such filters used. And there is another new word that is called pad 0. We'll see what do we mean by padding subsequent slides. Okay, then in this second level, so this level, there is also convolution layer. This is, they use 5 cross 5 convolution, stride 1, padding 2, and 256 such filters have been used. And pooling is in 3 cross 3 kernel and stride 2, and local response evaluation or LRN have been used. Next come the two only convolution layer, convolution 3 and convolution 4. This is just convolutions with these filters. It's 384 filters, 3 cross 6 kernels, stride 1, padding 1. So one we can see here, you can say that this dimensionality of filters, so channel is basically increasing. Here also convolution 4, that is 384 filters. Next come this convolution 5 and max pool 3 layer, that is this level, that is convolution layer 5, 256 such filter. This is 3 cross 3 kernel, stride 1 and padding 1. And max pool is basically spooling 3 cross 3 kernels. Then there is a 3 kind of 2 are fully connected layer. Another, this is also fully connected, but this is basically a softmax layer. So this is the very overall architecture of the AlexNet. Okay, so it basically is very good performance at that time over the conventional network. Now we just try to understand what are the different, what are the basic principles or basic outcomes of these different layers. So before that, we jump into these details discussions. We first to understand what is padding. Now padding in convolutional neural networks is a technique that adds extra pixel, that usually zeros, around the border of an input image or feature map before convolution. Now let's say there is a 3 cross 3 image patch and it is convolved with another 3 cross 3 convolution kernel. Now what happened? This thing, first this particular center of kernel pixel, that is placed here. Now if we put this here, this thing will happen. Now here, that is some values will come, and these values are not kind of initialized before. So what padding means, we put all zeros here. Similar thing happened here, happened here, happened. So we can, if you use padding kind of thing, this process we continue, then this is kind of the padding. If we convert 3 cross 3 with another 3 cross 3, the total, this, the effective, the receptive field, the actual receptive field become 5 plus 5. And these are the padding, because these values we don't know. So this process prevents the spatial dimension of the data from shrinking rapidly and preserve important information at the image edges. So if you do this convolution without this, that image edge pixels maybe get disrupted. So this is called padding. Okay. Now what we're going to understand, what is happening in the first layer. Now we can see the input image size is 27, 227 cross 227 into 3. Okay. And first convolution layer, they use 11 cross 11 kernel with stride 4. Okay. And padding, there is no padding is used. So this and such 96 filters. Now the question is, if we use this, what will be our output volume? What is the output dimensionality? We can use this. Now, if we have to calculate it, we have to calculate with our own n minus m by stride plus 1. So exactly same that we are going to do. That output size volume 227 is our capital N, minus stride 11 is our N. So this minus this by 4 because stride is 4 here. So it will come 54 plus 155. So you can see that this height and width is basically the 55 cos 55, and there is 96 such filters. So the channel size, so total number of channels is 96. So 96 different activation fields or activation maps, you can say. So it is basically 50 cross 55 cross 55 cross 96. Okay, so this is the how this particular convolution layer works. Now another question is that this is the 55 plus 55, that is what we have said. Another question is that what are the total number of parameters in these layers? Because how many parameters we have used 11 cross 11, say size of your convolution kernel. So that many parameters are there, and this is a 3 channels because this is 3 channels. So 11 cross 11 into 3, this is the actual convolution kernel, and such 96 kernels exist. So if we add, let's say 35,000 parameters, total number of parameters is 35,000 in this particular layer. Okay, so that is important to understand. And what is the output volume size? Here you can say that input image is 227 to 3, and out after convolution 50 cross 5, 55 to 50 96. Now next is pooling. Pooling is being done, and this is the 3 cross 3 pooling is done after we tried 2. So here also similar kind of 50 cross by 3 by 2 plus 1, so 27. So 27 is basically the output of this pooling. And interesting question is that what is the number of parameter in this? So output volume is 20 cross 27 cross 27 cross 96. Okay, the question comes, what will be the number of parameter at the pooling? Very interestingly, that is what is the number of parameters in the pooling layer, this particular pooling layer 1, so this layer. So interesting, it's a number of parameters is 0 because there is no learnable things here. We are just downsampling it. Okay, so this is the basic idea of this first layer, where one is convolution, one is maximum have been used. Now here you can see that the broader picture of the full, basically the full architecture, just what we have discussed. This is the first convolution layer. We use 227 minus 11 by 4 plus 155 number of, as we have discussed here, and max pooling with this 3 cross 3 filters with stride 2, we get 27 cross 27 96. That we can say. And this convolution is use 5 cross 5 filter. So if it is a 5 cross 5 pad, let's try 1 and pad 2 kind of thing that they use. So it becomes basically, if we these things, it will come, since it's a this is stride 1 kind of thing. So use a pad 2 already used, so it becomes this. Okay, 13 cross 13 to 56, and then it is normalized here, use 13 to 256 and so on. That is basically. So one important thing here, that what is the dimensionality of here, that basically 4096 the is fully connected layer 6 and 7, and there is a 1000 from there. This is softmax layer because it is a this is 1000 class, so this is 1000. It's basically works but softmax layer, and there is some details about how actually this paper on this paper that how actually this particular network has been trained. It is trained on GTX 580 GPU with only 3 GB of memory, and this is spread across 2 GPUs, half memories, and so on. Okay, that's so we understand that this is basically AlexNet. It's a very initial thing where, and this is the AlexNet in 2012, and you can see that this error rate, the top 5 error rate is basically error rate, how much it is almost 8 thing is basically 8% reduction in this error rate. So it is a substantial improvement over the SaloNet. Okay, so this is the basic of this visual recognition challenge, and this AlexNet become one of the major winner 2012 as a big milestone in this deep learning. So as we have seen that the CNN architectures are keep on improving in the basis of top 5 error rate for this ImageNet challenge. Basically, this is image recognition large scale visual recognition challenge, and what we can understand here that this is our AlexNet, which is 8 layers, and then we going to discuss VGGNet, and there is a certain difference of layers. The layers is increased, and we can see the error rate had decreased substantially. So that is very important to understand how this CNN architecture is being constructed with higher number of layers and definitely the improved performance. Let us start this VGGNet. It is been proposed by Simoyan and Gisserman in 2014. Now, one is the important innovation in this VGGNet is that the small filters and deeper networks. So what we have understand here that in this VGGNet there is a two version of VGGNet. One is 19 layer VGGNet, one is 16 layer VGGNet. Okay. So first criteria that the depth has been increased. So evolution from 8 layers from AlexNet, what we discussed before, to these 2 layers, 16 or 19 layers, that is VGG16 or VGG19, is a very, very popular convolution neural network. Okay. So what is the basic architectural innovation here? That exclusively use 3x3 convolution filters with stride 1 and padding 1 and 2x2 max pooling layers, stride 2. Now what we have to understand, how actually this particular architecture is going to improve over the previous state-of-art architectures. And the improvement of top 5 error rate that was in ZFNet 11.7 and this VGGNet is the state-of-art at that time, and that is down to 7.3%. So there is a clear more than 4% decrease in this error rate. So first of all, we understand what is the key contribution or key innovation of this PhysGNet. Okay. Before that, we just try to understand here. This is a kind of structure. Thus, you can say that this is a 3 by 3 convolution layer plus ReLU 64. Or even you can go there. The 3 different convolution layer are given in a stack. So you can say stack of 2 convolution layer or stack of 3 convolution layer, and that is bit different than the previous existing networks. So the question comes, why we use the smaller filter? That means 3 plus 3 convolutions. And what is the basic understanding or basic improvement or advantage of stacking of such 3 cross 3 convolution with stride 1 layers in the stack, the 3 cross 3? So what they proposed, or they claim, that the stack of 3 cross 3 convolution with stride 1 layers has same effective receptive field. That we have to understand what you mean by that, as a 7 cross 7 convolution. So first of all, we understand what is the effective receptive field of 3 cross 3 convolution with stride 1 the layers. So that we have first to understand. Okay. Now here there is a 3 convolution layers. We are basically denoting with 3 different color. This is a stack of 3 cross 3 convolution layers. Now what happened? First you please try to understand this kernel. If we these 2 kernel, if we convolve between them, okay, then what happened? It is what it will come. This kernel will come first. This portion come here, and then we just, since it is a stride 1, it will go by this way. So what actually happened, that if we do this kind of what we have seen in the in our previous slides, that padding operation kind of what when discussing, that same similarly this will come this kind of structure. And here you can see that since there is a one padding is there, so it becomes the 5 cross 5. Now you see that if 2 3 cross 3 are given successively, the effective receptive field become 5 cross 5, because these 2 are given in a row. Now if you put another over this, then the receptive field similar way coming another layer of this. So the things become 7 cross 7. So ideally, if what we can understand, that if 3 consecutive filter kernel or convolution kernel are stacked in this way, then the effective receptive field becomes 7 cross 7. And that is the one of the key motivation or key contribution of this paper or of this particular architecture. Now this is answer is 7 cross 7. Okay, so that we have to understand. Now we can understand that what is the effective receptive field of 3 cross 7 convolution with stride 1, that is 7 cross 7. Okay. Now what we have to, what advantage we will get? So it is a stacked 3 by 3 cross 3 versus single 7 cross 7 convolution. We can put in even in this case, we can put only 1 7 because this is triple layer 7. So what we have proved earlier, a stack of 3 cross 3 convolution layer with tried one has the exact same effective receptive field of 7 cross 7. So, but what advantage we get? Increased nonlinearity. If we use one 7 cross 7, there is only one nonlinear activation function was supposed to involved. Now here there is this stack of 3 cross 3 and such 3 filters. The stacked approach is deeper and includes 3 nonlinear activation layers instead of just one case of 7 cross 7, allowing the network to learn more complex features. So that is a very important advantage, and that makes this network much improved over the state of that time, definitely. Another important thing, the parameter, number of parameters. If the stacked 3 cross 3 layers is significantly fewer parameters, let there is a 3 channels, so is it 3 or 5, whatever, C channels. Now if you stack with the stacked version, then it is a 3 into 3 square to C square is 27 multiplied by C square. But if you go by the 7 cross 7, it's 7 square into C square is 49 C square. You can understand. There is the stacked approach reduced the parameters by approximately 45%. It's a huge improvement. So less parameters, so less costly, but more nonlinearity, more expressive power. Okay, and that is the one of the major improvement or innovation at the time of 2014 VGGNet. And you can see here that particular, this is just a architectural description how actually this particular layer is working. This is input is 224 cross 224. So this is 3 channel because this is the image input. So memory is basically 150K, and since it's the input, no parameter is being learned, so parameter is 0. So first convolution layer is 3 cross 3, 64 such convolutions. Parameters are there, 64 such kernels are there. So memory is 224 into 64. So it's 3.2 million parameter memory, and parameter is 3 cross 3 cross 3, 64. So 1728. Similarly, here also the memory requires 3.2 meg, and parameters is basically 36,864. And pooling layer, definitely that memory requirement 800K parameter, and so on. So this is the that we know very well in how these are some numbers that describe this architecture. Okay. The same year 2014, another very important network come into the picture, that is called GoogleNet. It has 22 layers, and the stop tier error rate becomes 6.7. So this is also a deeper network. So in GoogleNet 2014, proposed by Sajdi et al., this is a net. It has a computational efficiency is very important or very good for this particular network. So what is the primary features of this network? The significant depth, so it consists 22 layers, so even more than the VGGNet. Now, one key innovation of this architecture, this inception model, that we're going to discuss in next few slides. So they propose a concept of inception model in this particular GoogleNet. And another architectural difference that it contains no fully connected layers, unlike AlexNet. Another major advantage of this GoogleNet is that it uses only 5 million parameters. That is 12 times fewer than the AlexNet. And it is in this ImageNet challenge, that is the winner of this challenge in 2014 with 6.7% of failure rate. So these are the basic characteristics of the Google. Now, what we have to mainly understand, what do you mean by inception network? An inception network, like GoogleNet kind of, is a deep convolution neural network architecture known for its inception module. So basically a network with inception module is called inception network. So in that way, simplistically you can say GoogleNet also inception network. What do we mean by inception module? Now it processes the feature, so extract kind of feature. This is the previous level input, you can say input from previous level, and this is coming to the multiple scales of, so you can say 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution, and so on. So this inception module efficiently processes the features at multiple scales in parallel within a single layer. Now we can see here in this GoogleNet is something like this, that this module is one inception module. This one is another inception module, and it is been just arranged in this fashion. Okay, so what is the advantage of inception module? It helps reducing computational cost, that we will see later, while increasing depth and performance of the task like image classification. Now that also we try to understand how this inception net just make this particular inception net or GoogleNet more beneficial or more advantageous for mostly in image classification challenge. Okay. Now try to understand this from very naive architecture of this inception module. So this is a previous layer input coming from the previous layer, and what we have said, that is in parallel there is multiple scales of convolution kernels. So apply parallel filter operation on the input from the previous level. This is, and there is a multiple receptive fields for the convolution. Now there one question can be asked here: why multiple receptive fields matter? What is the role of receptive field? What is the role of smaller receptive field? What is the role of higher receptive field? Now we want to understand this from bit computer vision point of view. If you consider an image, in an image everywhere the pixel correlations are not same. Some homogeneous area, just for example, if there is a sky, well, there the pixels are very homogeneous in this area. Where in general we have observed that filter with higher receptive field be better choice, because the interpixel correlation is very high. But where there are some images, let's say there is some trees, some grasses, some forest kind of, but there is a lot of texture, or a very complex texture is there, where we can see the lower receptive field, that 3 cross 3 convolution, 2 cross 2 convolution, even 5 cross 5, these kind of smaller filter kernels is much effective. This is a bit in-depth things, but this is a very kind of heuristically understand. This is mostly true. So that's why what we are basically trying to do, that going to different receptive field, we can find that a different types of response from the similar patch. If a particular image patch is very, we can say the higher order frequency is high, then we can go for the smaller. If the low frequency component is high, then you can go to a bit higher receptive filter. So in this basis of this understanding, say we use this parallel multiple receptive field of different convolution layers, and there is then the pooling operation is also there, and ultimately after that we concatenate all the responses and together depth wise. So this is the very naive inception point. Now there is one problem here. Can you find what is the problem? Problem lies that we will see in this next slide, that what is the computational cost of this, because same input we are now doing multiple filter kernel and then concatenate. So you can see that here that this number of filters, let 1 cross 1 convolution 128, for 3 cross 3 convolution is 192, for 5 cross 5 convolution is 96, and so on. And let the module input is 28 cross 28 cross 256. This is channel numbers. Now if we try to find what is the dimension of this resultant or this activation map, this is 28, 28, 128, because this is 128 number of filters. This is 28, 28, 192. Use padding for that. That's why that this dimension is not changed. Similar, same 28, 296, 96 bit. And since the max pooling is 28, 256, similar. Okay, we're not downsampled here. So if we do that, how many operation is formed here? You can say for 1-to-1 convolution, this is 28 into 128 into 256. For 3 cross 3 convolution, 28 to 28 into 192, and this is 3, 3 into 256, because 256 such things. Now, what is the basic for 5 cross 5 convolution? 28 into 28 into 96 into 5,5 into 256. Why 256 is required? Because this is 256. So each convolution is 1, 1, 256, 3, 3 into 256, 5, 5, 5 into 5 into 256. So that's why this. So if you add all these three, then 854 billion operation. So it is a very, very expensive compute. Here we just what I said, that pooling layer is also preserved the feature depth, which means total depth after concatenation can only grow at the every layer. So what is the output depth? If you go the output depth, it is 28 cross 28 is 672, because we just add 120 plus 9, 192, 96, 256 and get 28, this 672, and this is 28 by 28, 672. So it is a very expensive. So the question is how we are going to solve this or reduce this computational complexity. To handle this computational complexity, we introduce another concept called bottleneck layer. Now, what do we mean by bottleneck layer? Bottleneck layer is basically designed to reduce the computational complexity and parameter count. How? They generally use the one-by-one convolution to reduce the channel depth. Let us understand by some visual examples. Now here you can see what we mean by one-by-one convolution. It is just if it is this 6,6, this image patch, whatever number it is, and this is the convolution, one-by-one convolution. It's just multiple. This just multiply the element with multiplication. This. Okay. So this. Now similar, if we same thing, only difference here is that this is also 6 by 6, but each convolution there, because this image or input as a channel depth is 32. So we have 1 cross 1, similar this, but only depth, channel depth is 32 is same. So what will happen? This is only one. We can got a 6 by 6 activation map. Okay. So exactly what it is happening here, that this is a 6 cross 6 into 32. This is, and it is basically fitted here, element wise element multiplication, and we end up with a for a particular position. It is, since it is 1 cross 1, it will, and this is a 6 cross 6, so all there will be a 6 into 6 responses. Okay. So pixel values from each 32 channels are multiplied with corresponding convolution kernel coefficient and series sum to get a 1 pixel the response matrix. So this is the response matrix or activation map. So what we going to get? This is 32. This is element wise multiplication and then addition. Got a 1 particular, and that all 36 position we slide, this window will slide, and we get all 36 position value. This exactly happened, and by virtue of this we get this, since it is a only single kernel. So this is only. Now if we get some multiple kernels, so let in this example there is a 4 number of kernels. Okay, so for 4 number of such kernels we get 4 activation maps. So that is important to understand here. And this is a 32. This dimension is 6 into 6 into 32. But here we use 1 to 1 into this is 1 by 1 by 32. And 4 numbers such, and this 4 number is our choice. Now how many kernels we are going to use, and we get the channel depth. It was before 32, now it is 6 to 6 into 4, because these are 4 activation maps. So this is from 32, it is 4, so 8 times it has been reduced. So in this way, this 1 cross 1 convolution operation can be used to reduce the dimensionality, mainly the channel width, and this is called bottleneck. Now we have to understand how these have been used in this practical scenario like this inception module. So 1x1 filters primarily used to reduce the depth dimensionality of layer while preserving the spatial resolution, height and width. So 28x28 is this. It is 192 previously, now is only 32 filters, so there is a substantial difference. So this is the way this 1x1 convolution used as a bottleneck layer. Now with virtue of this understanding, on the background of this understanding, we try to understand how this inception net, it is the naive inception net, and that is 84 number of operation, how this can be improved or reduce the number of parameters. Okay, that we are going to understand. Here, what we going to do from the previous layer, we put this 1/n convolution here. Now it is initially 256. Now is 1,1 convolution with 64 filters. Now it's become 28,2884. Now substantially reduced. From this also substantially reduced 28 to 20. Okay, and here also can 28 to 28 to 56 because it's a max volume. And but here also we use bottleneck layer. So here you can see that these bottleneck layers has been used to get this depth to from 256 64. It is also 64. It is also 264, and since here 128 is 128. Now what happened? Since we use after that we use 192 filters of 3x3, it's become 28 to 192. 28 to 96 because it's 96 and it's 64. Now if we add it up, we get what? 28 to 28 to 480. Now it is substantially reduced. Initially it was 672 and now it's 480. And if we have calculate these values, we get total 358 million operation. Okay. If you see, if we compare both this, it was 672, now it's 480 using this bottleneck layers. Okay, initially that was 854 billion operation, now it's become 358 billion operation, substantially reduced. So compared to 854 operation for naive version bottleneck, can also reduce depth to 358 million operation after. So that is the way we can use bottleneck, and that is one of the key innovation of the GoogleNet. Yeah. So in this lecture, what we have basically introduced the CNN architectures. We start with LANet, then we discuss the AlexNet, what is the major characteristics of AlexNet. Then VGGNet we have used, we have discussed, and GoogleNet in inception module at the bottom. Snake lecture we are to discuss how we can optimize our convolution network, because convolution neural network that what we have observed, there is several layers, several hidden layers are there. So there is some issues of the deeper network. What are the issues and how these issues can be handled? That will be the topic of our next. Thank you very much.